Hey guys, this video is on pressure and the gas laws. So we'll start out by talking about pressure. Pressure is defined as force over an area. P for pressure, F for force, A for area. The IUPAC or SI units of force are newtons, and 1 newton is 1 kilogram meter per second squared. Because pressure is force, newtons, over an area, which will be meters squared in our SI units, you get newtons over meters squared ends up working out to be kilograms per meter second squared. And that's the definition of one of our units of pressure, pascals. 1 pascal is equal to exactly 1 kilogram meter per meter second squared. So let's look at how we measure pressure. So this is important to us for 2 reasons, at least. One is it shows where some of our units come from of pressure, and it shows how we measure the pressure of a gas in the lab. So let's start out with this picture on the left right here. So this is showing a pool of liquid mercury with a glass column that's closed at the top, open at the bottom, inverted in here, and in this tube right here there's a vacuum. There's not even any air, nothing up here. And so what happens is the air above us, the atmosphere, is pushing down. Now it's pushing down evenly all over the surface of this liquid mercury. But if there's anywhere that's not pushing back with the same pressure, with less pressure, that liquid mercury will go there. And well, at the base of this column, it's open, it's not pushing back because there's a vacuum in here. So the liquid mercury rises up this column, and it keeps going as atmosphere presses on it. But as this column of mercury gets higher and higher and higher, gravity's pulling it back down until the force exerted by this column of mercury due to the force of gravity, or the acceleration due to gravity, is exactly balanced by the pressure of the atmosphere pushing down on the liquid mercury. And once you reach that point, it stops moving and it stays at a certain height. So when you first put it in there, column goes up and up and up and up and up, and then it stops once it's balanced. Now if you change the atmospheric pressure, the height of this column of mercury changes. If the atmospheric pressure decreases, the column will go down. If the atmospheric pressure increases, the column will go up. And so the height of this column of mercury is a measure of the atmospheric pressure. That's where you get units of millimeters of mercury, inches of mercury, centimeters of mercury, and torr too, it ends up. Now the pressure exerted by this column of mercury is given by this little equation here, P equals HdG. H is the height of the column, how high it rises up. D is the density of the liquid in there. This is for any liquid column. G is acceleration due to gravity. Notice if you look at this, nowhere in here does it talk about how wide across this column is. It could be a mile across or a millimeter across, and the same equation applies. The reason is pressure is force over area, so we're dividing by the area. So no matter what the area is, it divides out. It's per unit area. So in this equation here, a couple things to look for. Density, it has to be in units of kilograms per meters cubed, not grams per milliliter or centimeters cubed like we're used to using in chemistry. And G, the acceleration due to gravity, there's the number, 9.80665 meters per second squared. So we're going to use that in just a minute. But let's look over here at these manometers. So like I said, we use these to measure the pressure of a gas, usually involved in a chemical reaction. So there's 2 types of manometers, closed tube and open tube manometers. Let's look at the closed tube manometer first. This setup here has a container for the gas that's going to be involved or is involved during a chemical reaction. And it has a glass tube over here, shape of a U, and this other end over here, it's closed over here. On this end, it's also closed to the atmosphere, and there's a vacuum. There's not even any air in here, nothing in here. And so what happens is when we start out, before the gas is evolved in the chemical reaction, there's no gas in here, and so the height on each side of this U is the same. They'll be balanced, right? Because gravity is the only thing affecting the height of the column of mercury on either side. But when the gas is given off during the chemical reaction, it's going to press down here, pushing the column up of mercury on the other side up. How high that column rises compared to where it is on the other side, that's a measure of the pressure of the gas. The pressure of the gas is just equal to that height, which is millimeters. Real easy to measure. Take a meter stick, see how many millimeters it is, millimeters of mercury. Now, in an open tube manometer, what's different is that the column on the right here is not close to the atmosphere, but it's open to the atmosphere. So the atmosphere is pressing down here. So when this gas is given off, it has to push against two things, the mercury and the atmosphere. So the pressure of the gas will be equal to the pressure due to the column of mercury plus the atmospheric pressure. So if you're doing a manometer problem, just have to be careful about which kind of manometer that you have. All right, so let's go look at these. So units of pressure. These are different units of pressure that we use. You should write them down, memorize them, or put them on your card. And the way this is set up is that a really common unit of pressure that we use is the atmosphere, ATM. Exactly 1 atmosphere is equal to each of these things. That means each of these things is equal to each other. So 101,325 pascals, we saw those, which is the same as 101.325 kilopascals, which is the same as 760 millimeters of mercury. The 760 is an exact number, these two are not, which is the same as 760 torr. So millimeters of mercury and torr are the same thing. 1.01325 bar, not exact, 14.70 psi, pounds per square inch. Probably if you look on your tires, you'll see psi there. Or 29.92 inches of mercury. None of these are exact. The only exact numbers are the 1 atmosphere and the 760s. So these are conversion factors, guys. Any one of these is equal to the other. So let's do an example. We want to calculate the pressure at the base of the column of gallium. Gallium's liquid at just over room temperature, so this is liquid gallium. Its density is given right here, 6.095 grams per centimeter cubed, and the height of that column is 847.2 millimeters. And so we want to calculate the pressure at the base of this column, so P equals HDG. So why don't you guys go ahead and work this problem out, and when you get an answer, come on back. Welcome back. So P equals HDG. First thing I did here is I took that millimeters, moved the decimal 3 to the left to convert it to meters. G is just 9.80665 meters per second squared. And the density, remember we have to have the density in kilograms per meter cubed, and we're given it in kilograms per centimeters cubed. So this is just converting the density to kilograms per meter cubed, and I get 6,095 kilograms per meters cubed. Now I can plug in to the P equals HGD, and notice how the units work out. Get meters times meters is meters squared, meters cubed on the bottom, so we end up with meters to the first power on the bottom, kilograms on top, second squared on the bottom. And I end up getting this number right here. So the units, kilograms per meter second squared, remember that's the same as a Pascal back in the beginning. We saw that, right? So the pressure, it's 5.0638 times 10 to the 4th pascals. And what I did here is I just converted it to atmospheres. In chemistry, we use atmospheres a lot more commonly than we do pascals. And so all I did is took a conversion factor from that chart I showed you. 1 atmosphere is equal to 101,325 pascals. And I end up getting 0.4998 atmospheres. All right, the ideal gas law. So if you remember back from the kinetic molecular theory video, an ideal gas is one that obeys the kinetic molecular theory. It's basically the particles themselves occupy no volume, take up no space, and they do not interact. Those are the primary parts of the kinetic molecular theory that apply here. So this describes the behavior of any ideal gas. It says its pressure times its volume is equal to the number of moles, N, times some constant R, the gas constant, times its temperature, PV equals nRT. Units, pressure can have different units, but whatever units of pressure we have are going to determine the value of R, because it has different values depending upon what units of pressure we have. V is a volume, it's always going to be in liters, N is always moles. Now temperature has to be in Kelvin, so watch out for that. That catches people at first. Usually we measure temperature in Celsius in the lab because most of the thermometers we have are in Celsius. So we have to convert it to Kelvin. R is the gas constant, and we'll see that right now. So the gas constant can have, has different values depending upon what units you use. 0.08206 if the units are liters atmospheres per Kelvin mole. 62.36 if the units are liters torr per Kelvin mole. Real quick, remember torrs are the same thing as millimeters of mercury, so you could write 62.36 liters millimeters of mercury per Kelvin mole. Same thing. Or 0.083145 liters bar per Kelvin mole, 8.3145 joules per Kelvin mole, 1.9872 calories per Kelvin mole. So know these values for R. None of them are exact. So here's an example. Calculate the molar mass of the gas. If we have that many grams of the gas, 2.803 grams, it has a volume of 923.6 mils, temperature 22.7 Celsius, and a pressure of 789.4 torr. So why don't you guys work this out, and when you get an answer, come on back. Welcome back. So first of all, I'd ask for molar mass, and nowhere in the ideal gas law is there a molar mass. Well, but if you look at what molar mass is, it's just the mass divided by the moles, grams per mole. And we're given the mass in the problem, this number right here. So if we can find the moles of that gas, we can just take the mass that we're given, divide by that number of moles, and we'll have our answer. Well, in the ideal gas law, there is a variable for the moles, n. So if we rearrange the ideal gas law, solving for n, if we can get that, then we have the denominator here, and we're good to go. We're given the pressure, right there. We're given the volume. I converted it to liters already. We know R. Because the pressure's in torr, I'm going to use 62.36 liters torr per Kelvin mole. Now you could, if you wanted to, convert the pressure to atmospheres and then use 0.08206 liters atmospheres per Kelvin mole, and you'll get very close to the same answer, but why? And the temperature, we were very careful to convert that to Kelvin. So now we have everything. We can just plug into the ideal gas law, PV of RT, and we get this many moles. Now we can use that, plug it into the definition of molar mass, take the grams that were given, divide by the moles of the gas we calculated, and we get 70.93 grams per mole. All right, so here's another form of the ideal gas law it's pretty cool when you think about what it can do for you. And let's look at it here. So starting with the ideal gas law, PV equals nRT. Now, another way of writing N, the moles, is to take the mass in grams and divide by the molar mass of the gas in grams per mole, because you see the grams cancel, moles comes up on top. That's how many moles. If we substitute this in for N in the ideal gas law, it looks like this here, and then cross multiply, basically take the molar mass over here and the volume down here. Now, real quick, here I just wrote M instead of M period for the molar mass because we don't want too many letters floating around. We get this form of the ideal gas law. But, we have mass over volume here. Remember, that's density. Density is mass over volume. So we can just write a D, the density of the gas here, and now we get this form of the ideal gas law, PM equals DRT, where M is the molar mass of the gas in grams per mole, and D is the density. Notice it has to be in grams per liter. Watch out for that, because we're used to grams per milliliter, but it has to be in grams per liter for the units here to work out. Okay, here's why this is cool. We can measure very easily the pressure, the density, and the temperature of a gas. Temperature, stick a thermometer in it. Density, just weigh how much a certain volume of it weighs. Measure how much a certain volume weighs, mass and the volume. Pressure, different ways. It's pretty easy to measure the pressure of a container of gas. So these are three macroscopic variables that we can measure really easily. But when we do those, we can solve for the molar mass. So we can get a microscopic property, the mass of the molecules, by measuring these macroscopic properties. It's really pretty cool, I think it is. So let's do an example. So we want to calculate the molar mass of a gas. If its pressure is that 832.1 millimeters of mercury, its temperature is 23.7 Celsius, and we know from probably a different part of the experiment where we took a certain volume and we measured how much the mass of the gas in that volume weighed. It's 1.978 grams per liter. So why don't you guys go ahead and work this problem out and come back when you're done. Welcome back. So we're going to use, because we're asked for molar mass, we're going to use this equation right here, and we're given density. Rearranging this, solving for the molar mass, dRT over P. We're given the density, grams per liter. Pressure, 832.1 millimeters of mercury. So I'm just going to use this value for R, 62.36 liters, millimeters of mercury per Kelvin mole. Remember, that's the same as torr. And temperature, of course, we made sure to convert to Kelvin. All right, so we have all these guys plugging into the equation, density, R, T, P, and we get the molar mass, 44.20 grams per mole. That's pretty cool. All right, combine the gas law. So here, it's to talk about this, we're going to imagine we have two separate, different containers. There's an ideal gas in each of those, and they're under different conditions. So in container 1, the pressure is P1, the volume is V1, the number of moles is N1, and the temperature is T1. So we can write down the ideal gas law for the gas in container 1. P1 V1 equals N1 R T1. Likewise, for container 2, the pressure is P2, volume is V2, number of moles is N2, and the temperature is T2. So we can write this down, P2 V2 equals N2 R T2. Now, look at this. If we rearrange each of these equations where we get R on one side, everything else on the other, we get for gas 1, P1 V1 over N1 T1 equals R, gas constant. For container 2, P2 V2 over N2 T2 equals R. Well, they're both equal to the same thing, but R is the same, right? So that means that the left-hand side of the equal sign must be equal to each other. That is the combined gas law. P1 V1 over N1 T1 equals P2 V2 over N2 T2. So now, the clue that tells you that you are in a problem where you want to use the combined gas law is if something changes. If you have one set of variables and then one or more of those changes. By variables, I mean PV, and or T, PV, and T. So once you realize you're in combined gas law territory, the first thing to do is write down the combined gas law. P1 V1 over N1 T1 equals P2 V2 over N2 T2. And then anything that doesn't change, that's held constant under both sets of conditions, cancel it out, cross it out, get rid of it, because it doesn't change, it's gone. There's basically two ways that you'll know that from the problems you'll see. One, you're told that something's held constant. One or more variables is held constant. The other way is that you're not given any information at all about that variable. If you're not told anything about a variable, that means it's not changing. So once you've gotten rid of anything that doesn't change, you have a simplified equation. Now, real quick, in your textbook and in almost every textbook, general chemistry text in the gas chapter, you'll see all these smaller laws. They call them Avogadro's law, Gay-Lussac's law, all these, and all they are is variations of the combined gas law with different things are held constant. So I don't even talk about those, because if you know how to use the combined gas law properly, you can do any of those problems just using this. There's no need to memorize all that stuff. All right, so anyway, once you have isolated the variable you're looking for, by rearranging the equation, doing the algebra, just make sure the temperature is in kelvins. But the other variables, as long as the P1 is the same unit as P2, V2 is the same unit as V2, it doesn't matter what those units are. So here, let's do a little example. So we have two gases in two separate identical containers. First container, we have that many moles, 4.125 moles of gas, temperature is 24.8, pressure is 2.142 atmospheres. In the other container, the second one, we have that many moles, 3.994, pressure is 2.547 atmospheres, and we want to find temperature of the gas in the second container in degrees Celsius. Why don't you guys go ahead and work this out, and come on back when you're done. Welcome back. So, it's a combined gas law problem. We knew that because we had different sets of conditions. So I write down the ideal gas law. I eliminate anything that's not changing. The only thing that we were not told anything about is the volume. We said they're identical containers, so that kind of tells you that they're the same volume. So we got rid of the volumes, and what we have left is this equation right here. P1 over N1 T1 equals P2 over N2 T2. Next step, rearrange this, solve for what we're asked to find. We want the new temperature, that's T2, so it comes up top over here. N1, T1 goes in the top over here, and we get this right here. Next thing, now what I always do, and I really strongly urge you guys to do this, really, it just takes a few seconds and it will save you so much grief, trust me. List the value for every variable, P2, N2, a P1, T1, N1 in this case. If you don't, it's very, very easy, trust me, I know from experience, to get them mixed up and put them in the wrong place. So I went back to the problem and I listed every variable, what it is. So now all I have to do is substitute in for each of these, P2, N1, there, T1, there, N2, right there, and P1, right there. So I put those in and I get 365.9 Kelvin. But because we were asked for the temperature in Celsius, we just subtract 273.15 from our answer to get 92.8 degrees Celsius. Now, just real quick, even though we were given the initial temperature in Celsius and we wanted the answer in Celsius, we still had to convert it to Kelvin to do the problem. If you don't do that, you'll get the wrong answer. So just kind of make a little note to yourself, okay? Because it's pretty common for people to do that at first. All right, one last thing. Standard temperature and pressure, STP. This is just an abbreviation, STP, for standard set of conditions. The temperature is exactly 273.15 Kelvin, and the pressure is exactly 1 bar, which is exactly 100 kilopascals. Now, before 1982, this was defined differently. The temperature was 273.15 Kelvin, but the pressure was defined as exactly 1 atmospheres, which is different. 1 atmosphere is 1.01325 bars, so that's not exactly the same. It's different since 1982. However, every chemistry textbook that I've seen at the general chemistry level, at physical chemistry, they get it right now, but they still have the old definitions. That's not right anymore. The next thing is the standard molar volume, just the volume of exactly 1 mole of an ideal gas at STP. So if we just use the ideal gas law, solve for V, Vm stands for molar volume, exactly 1 mole. There's R, I use this because we have the pressure in bars. Temperature is exactly 273.15 Kelvin, exactly 1 bar. We get the molar volume of an ideal gas is 22.711 liters. Now, if you use the old definition, 1 atmosphere, you get a slightly different number. You get 22.41 liters. But that's not right anymore. This is the molar volume of an ideal gas under the current modern definition of STP. That's all there is to it, guys.